Hello everyone. In this video, I will show you how to calculate standard deviation using an example. In the process, I will also touch on the differences between the population and the sample. Standard deviation is a measure of how spread out the numbers are. Have a look at the examples here. These are both normal distributions. They have the same mathematical mean, but look different from each other. The first one has a high standard deviation, and the numbers are spread out further away from the mean. The second one has a low standard deviation, and the numbers are clustered closer to the mean. Here's another way to visualize the same idea. Let's say we have a class of 5 students, and they all took the same test. In the first example, some people did really well, and some not so much. In the second example, they were all in a very similar range. The average score is, the mathematical mean is the same, but the first example has wider spread of scores. This one has a higher standard deviation, whereas the second one has a lower standard deviation. Okay, standard deviation is the square root of the variance. Simple enough. So how do we work out the variance? Variance is the squared differences from the mean. Let me break it down. I'm going to stay with the test score example. Let's say these are test scores from a class of 5 students. We have the test scores from all 5 of them. That means what we have here is a population, not a sample. The capital N stands for the population size. N equals 5 because we have 5 students. And the average, or the mathematical mean, is 80. This Greek letter mu represents a population mean. We're interested in how far or close the data points are from the mean. So I'm going to start by measuring the distance from the mean. So the first student had the score of 90. The distance from the mean is 90 minus 80, which is 10. The second score is 95. 95 minus 80, which gives us 15. I'm basically subtracting the mean from the score. If you like to express this in a formula, I'm basically doing x minus mean, where x is the individual test score. So we're doing this for the first test score, x sub 1, x sub 2. Okay, I'll carry on with the rest of the students. We had 85 here. 85 minus 80 equals 5. 60 minus 80, which is negative 20. And we have 70 minus 80. This is another negative number, that's a negative 10. Now, I'm trying to work out the average of all these distances, so I'm going to add them all up and divide it by the number of test scores, which is 5. Okay, can you tell me what I'm doing wrong? Let's see. 10 plus 15 is 25. 25 plus 5 is 30. And on the negative side, we have negative 30. Hang on, we get a 0. This is not good. You might have spotted this already, but the reason for this is some of the data points are below the mean, and these distances are negative numbers. That's kind of how an average works. Some numbers are above the average, whilst others are below the average. If you add up all the distances, they all cancel out each other. So how can I go around this problem? I don't want any negative numbers here. So what we can do is we can square the differences. If you square them, the positive numbers stay positive and the negative ones will become positive. Okay, let's change the formula to x minus mean squared and go through it again. So we have 10 squared is 100, 15 squared is 225, 5 squared is 25, negative 20 squared is 400, Negative 10 squared is 100. Okay, we got rid of all the negative signs. This time they won't cancel out each other. We ended up with very large numbers, but that's okay. We're going to adjust later when we square root the whole thing. For now, let's add them all up. 225 plus 25, that's 250, and we have 100 plus 250, that's 350, and we have 500 here. 350 plus 500, that's 850. Next, divide it by the number of data points in the population. We have 5 students or 5 test scores in this population, so 850 divided by 5, which gives us 170. Okay, so now we know the variance of this population is 170. Does that mean the average difference from the mean is 170? That doesn't seem right. We're talking about a test where the top student scored 95 and the lowest score was 70. That's a range of 25. In fact, 170 is the average of squared differences. Remember, we had to square each one of them to get rid of the negative signs. This is a good time to make an adjustment. And that's why the standard deviation is the square root of the variance. The square root of 170 is about 13. Okay, I think we have everything we need to build a generalized formula. I'm going to start with the variance. If you remember, we started by taking the difference between an individual score and the mean. And the population mean can be represented by this Greek letter mu, and we squared the difference for each one of them. And then we added the squared difference n times, where the capital N is the size of the population. And you can add this notation to clarify that we started from x sub 1. So we went from x sub 1, x sub 2, and all the way up to x sub n. And don't forget to divide the whole thing by n. Here we are. This is the formula for the population variance. But what we're really interested in is the standard deviation. The standard deviation for population is represented by the Greek letter sigma. To get the standard deviation, you simply square root the variance. So I add the square root for the whole thing. Here we are. This is the formula for the population standard deviation. If you're wondering why I keep saying population, that's because the formula for standard deviation is slightly different when you're dealing with a sample. Okay, what I'll do is I'm going to copy and paste this, and I'll make a few changes. First, the sample standard deviation is usually represented by the letter S, the capital letter S. And the mean of a sample is represented by the symbol x bar. For the sample size n, lowercase is used. Capital N is for population, lowercase n is for sample. So far, these are all changes in the notation. The most fundamental difference in the formula is this. Instead of dividing the whole thing by n, when we're dealing with a sample, you divide it by n minus 1. This is called Bessel's correction. The reason for this is, if we divide the whole thing by n, it tends to underestimate the variance. In other words, the sample variance tends to come out smaller than the true variance of the population. So we need to make an adjustment, and it turns out dividing it by n minus 1 is a good way to correct for that bias. Hopefully, you feel comfortable working out the standard deviation yourself by now. If you'd like to know more about why we divided by n minus 1, I'm going to do another video and go into a little more detail.